Well, thank you for joining another lecture for Introduction to Computer Graphics. Now, we've been talking about animation in computer graphics, and we spent a bit more time talking about physics-based animation. We're going to spend even more time on that topic today. And we're going to cover simulation in computer graphics. Right? This is going to be about physics-based animation. And I'm going to talk about all sorts of different tools that are used in computer graphics. But this is not intended to be a comprehensive overview of every simulation-related thing in computer graphics. But we're going to cover some of the basic stuff. I'm not even going to talk about every simulation-related stuff that I've done in computer graphics. But we're going to cover some more common things, some more fundamental things that happen in computer graphics. Not everything. And I'm going to cover these at a relatively high level. Instead of going into too much detail of what exactly happens, I would like to give you a high-level overview of how the simulation problems are solved in computer graphics. And I think the topic that we covered last time, talking about the details of how mass spring simulation is handled, will give you enough of a background for you to sort of understand the technical stuff that I'm going to talk about today. But the technical stuff is going to be relatively limited. So this is going to be, in terms of technical content, it's going to be a relatively light lecture. But my whole intention of this is to give you a general idea about how simulation-related stuff is handled in computer graphics. All right, so let's start with our first stop. We're going to start with, over here, rigid body simulation. So this is a video from a relatively recent NVIDIA demo. So let's watch this video. Here, as you can see, the player is throwing some balls on top of some rocks, and the rocks are colliding with that ball and bouncing around. Now we're going to jump into this bulldozer. There it is, and then we're driving the bulldozer into these rocks. And of course, there's going to be some collisions. We're going to push them around. So as you can see, there are quite a few objects here. They're colliding with each other, stacking on top of each other. This is PhysX, NVIDIA's GPU rigid body simulation system that can handle rigid bodies. So the concept of rigid body simulation and things like this is not very new. Now, this is a relatively recent demo, and what's impressive here is that this is real time, and there are lots of rocks here, or lots of rigid bodies. That's what's impressive here. But the whole concept of rigid body simulation actually has been around in computer graphics for quite some time. Even real-time rigid body simulation has been around in computer graphics. But nonetheless, I really like this video. I wanted to show it to you. If you only knew how difficult it was for what I had to do to get this footage for you guys, but I hope you enjoyed it. Anyhow, so this is the gist of it. All right, let's move on and talk about what's going on here a little bit. Right. So we talked about mass spring simulation, not rigid body simulation. And with mass spring simulation, we had particles, right? So each particle had a mass, and they were point particles. That's what we had with mass spring simulation. With rigid body simulation, instead of particles, we have rigid bodies. And they're a little bit different, right? So a particle has a position, and that's it. But a rigid body has a position, and it can also rotate around that position, right? So I need to know not just its position, but also its orientation. So for a particle, we only have its position. That means it only has 3 degrees of freedom. What are those 3 degrees of freedom? Its position in X, Y, Z. You can think about it that way. You can use a different sort of coordinate frame for this, but in 3D, a particle, a point particle, will only have 3 degrees of freedom, however you represent that, whatever coordinate frame or representation you use, it's going to have 3 degrees of freedom. A rigid body is going to have position and also orientation, basically rotation. So I'm not assuming that it's not squishy. You cannot scale it down the rock. You can only rotate it around. If that is the case, I can rotate it around X, Y, or Z, or a combination of them. So it's going to have 3 degrees of freedom for position, 3 degrees of freedom for rotation. So it's going to have in total 6 degrees of freedom. So if a rigid body is quite a bit more complicated than a particle because of that. So when you think about how a rigid body interacts with its surrounding, for example, if I just drop this and it just collides with some object, it's not going to just bounce back up, right? It's going to, the impact of this collision is going to make this rigid body rotate around and maybe continue falling, right? So it's the collision events are a bit more complicated here. So what will define what's going to happen to this object when there's a collision is where exactly this collision happens. In this case, over here. So there's going to be collision forces applied at this point in the normal direction. So there's going to be some force pushing it up in this direction, and that's going to create a rotation of the rigid body, right? So we kind of need to compute not just the force that's applied to this object, but also the torque. Torque is the rotational force, basically. We also need to compute the torque that is applied to it. Actually, in rigid body simulation, it's more common to use what we call impulse-based collisions. So impulse-based collisions basically skip the force term and defining an acceleration and then acceleration. When you have force term, force defines an acceleration, acceleration defines the change in velocity. So impulse-based collisions instead define an impulse instead of a force. That impulse directly modifies the velocity or the rotational velocity, right? So like we directly modify the velocity based on the collision. That's the more typical thing to do. It turns out to be a bit more stable than having a force-based formulation of what happens here. Actually, that's pretty much what I suggested that you do for the collisions with our mass spring system. So the mass spring system you will be implementing, where we're modifying the velocities when there's a collision, that's actually an impulse-based collision technique. Right. And so depending on where this object collides, it rotates around. So because of that, handling rigid bodies is quite a bit more difficult than just handling sizeless particles. Another thing about rigid bodies is that this rigid body could be landing on the surface maybe, and it's like in this example there are collisions in two places, right? So that it's touching the surface in two places. So it is stable here, right? It's not gonna fall in any direction. But if you were to compute this, it is possible that maybe I find the collision here at this point in this time step. And in the next time step, I'm going to resolve this collision in this time step. And in the next time step, I find the collision with the other one. So I might be finding these collisions not exactly at the same time, but one after the other. And if things like that happens, then this object will be just, vibrating like this nonstop, right? So as I keep simulating this object, it's going to be vibrating like this. Now, this vibration can be very small, so you don't actually notice it, but your simulation system will be dealing with that constantly. And it's very, very difficult to make sure that these two collisions in two places happen exactly at the same time, exactly at the same time step, right? They may or may not happen, and these sort of things are actually very, very common. It can happen, even if they're not visible. Now, if this is not visible, maybe you don't care. And maybe it's okay. Like a simulation like this, for example, if you don't see this vibration, if it's small enough that you can't see, maybe it's okay, maybe you don't care. But in a bigger simulation scenario, like the example that I showed you in the beginning, that's the video with lots of rigid bodies, dealing with this sort of thing can be quite expensive, right? So I have repeated collision events happening, and what should happen is that I would like this motion to stop, right? This is what I would like to happen. Basically, I would like my simulation to produce absolutely no motion in this case. So instead of simulating this and keep getting this sort of unnecessary motion, unnecessary computation, and unnecessary instability, what we typically do with rigid body simulation is that we define a rest in contact condition. So if we detect that an object is not moving at all, then there's really no point in simulating this, right? And we say that, oh, this object is rest in contact, it's going to stay there until something happens to it, right? So it's going to be an object that's rest in contact. Now, there are different ways of checking whether an object is rest in contact, and if it's rest in contact, if you decide that the object is in rest in contact state, then you don't have to simulate it anymore. You can just stop simulating it until something happens to it. For example, until we have another object that collides with it, and at this point we can say, oh, something hit it, so maybe this object is going to move now. Or maybe not. Maybe there's going to be enough friction to keep it around and it's not going to move. But of course, just like I have an object rest in contact on a stationary collision object here, it can also be rest in contact on another object, right? So these two objects can be rest in contact, and actually I've just put two objects on top of each other, and this is the concept that we call stacking. This is quite a bit of a difficulty here, because I have an object that's rest in contact, it's on an object that's also in rest in contact, right? So if I sort of hit this object with something, then the rest in contact situation for this object must be modified as well. So the simulation sort of needs to keep track of this stack, and if anything at the bottom of the stack changes state, it's not rest in contact anymore, I kind of need to modify the other object in the stack accordingly. And the stack can be quite large, right? I don't have to have a single object, but just two objects. I can have quite a few objects stacking on top of each other. This sort of thing happens. Like in the example that I showed you, there were piles forming, and those piles were very much like this, right? And if you want to have an efficient simulation, of course, you don't want to continue simulating these piles when they're rest in contact. All right, so these are some difficulties related to rigid body simulation. Another very, very important topic is the simulation of articulated rigid bodies. So an articulated rigid body, for example, you can take a rigid body like this, like a rod. It's just a rigid rod. And I take another rigid rod here, and I connect them here at this point. I'm adding a joint constraint to these two objects. So now this turns into an articulated rigid body, as we call it. And this system, this can bend like this, right? But otherwise, this object will move as one thing, right? Because of this joint constraint over here. So if we look at this system, let's try to count the degrees of freedom of this system. Now I have a rigid body here that has 6 degrees of freedom, just like any other rigid body, right? And I have another rigid body here that should also have 6 degrees of freedom. But I also have some joint constraints here. Now the joint constraints will not permit rotations around certain angles. So it's not going to permit rotations, it's only going to permit rotations around one direction. So 2 of these rotation directions will not be permitted. That means it's sort of removing 2 degrees of freedom from the system, right? It's also, these 2 bodies are also attached together at this joint. So this body cannot move independently from this other body, right? So its position is not really independent. So I need to remove its position degrees of freedom as well, right? So if you count all of these degrees of freedom, like 6 here, 6 there, and 5 removed, I end up with 7 degrees of freedom, right? That's one way of looking at it. Here's maybe an easier way of looking at this. You can think of this as just one object. Now, if this were a rigid body, I know that it would have 6 degrees of freedom, right? It can move around and it can rotate around. That's 6 degrees of freedom. This object is not a rigid body, though. It can deform. How can it deform? It can deform around this joint. So around that joint, I have 1 additional degree of freedom because it can bend like this, right? So if you look at this, its total degrees of freedom will be 7. So basically, we end up with the same thing, obviously, right? These sort of rigid, articulated rigid bodies are very, very common in computer graphics, and most of our rigid body simulators can handle different forms of articulated rigid bodies. For example, we can have engine parts like this. This is not a simulation; it's just an animation of what this object part is doing. But what this the machine component is doing. But it could be a simulation as well. So I could have a joint constraint that only allows rotation around this joint. These sort of articulated rigid bodies are also used for ragdoll simulations. Again, this is not a simulation, just an animation, but you get the idea. They're used a lot for vehicles. Also, the vehicles are modeled as articulated rigid bodies. Right? And in these sort of simulation scenarios, all of these components are actually rigid bodies, but they are connected with different types of joints. And those joints have different sort of degrees of freedom. They allow different types of relative motion. So for wheels, we know that they will permit rotating around one direction. For joint angles, so for the ragdoll simulation, we have joints that can move differently, so they can have different constraints. They typically have position constraints, but they don't have to. Sometimes we have sliding joints that can happen as well. So we have all sorts of different joints. Now, when it comes to simulating these sort of things, these joint constraints can be applied as different types of forces that hold the objects together. I can apply them as, for example, if I want to keep two things together, I can apply a spring force with zero length spring. So whenever they move apart, the spring force will pull them back together, right? So that would be one way of applying these constraints, and that's a relatively common way of handling these constraints. But they can also be applied as hard constraints, that I can define my simulation system and I can remove the degrees of freedom in my simulation system that cannot be modeled by my articulated rigid body system. So if I remove those degrees of freedom from my simulation, I guarantee that my articulated rigid body will always obey those constraints, or will always obey those joint constraints. So this simplifies the numerics of the simulation a little bit, but of course it sort of makes the implementation of the simulation a bit more complicated. The implementation becomes a bit more complicated, but then you get additional benefits like efficiency. But it really depends on what kind of numerical tools you're using. So there are benefits to either approach here. So just wanted to say that there are different ways of making sure that these joint constraints are satisfied so that the articulated rigid body actually acts like an articulated rigid body. All right, enough about rigid bodies. Let's move on. So if I don't want to have rigid bodies, what kind of bodies do I want to have? I want to have probably deformable bodies, right? So let's look at deformable objects. So here's an example deformable object simulation. Now this is from a recent work that we're actually working on. It's the legs are deforming. That's what's important. And the particular animation, the particular simulation method used here is what's called a finite element method. So I would like to talk about the finite element method a little bit. So the finite element method is one of the methods for simulating deformable objects. And the way it works is that we take an object and we discretize it in one way or another. We typically, for a 3D object, trivialize it. We form a whole bunch of tetrahedra out of this object. So if I were to cut this, it will look like this, right? So I have a whole bunch of, like, each one of this is actually just a tetrahedron, right? And the reason why we use this is simplest 3D element that we can form. And there are various ways of handling this. Like, you can think of this like a triangulation in 3D, right? We kind of need to worry about the volume, and this is like the basic element that we typically use. We don't have to, but we typically use something like this. Now, I'm going to show you what's happening in 2D, like an example like this. Let's say that in 2D, I can implement finite element method in 2D as well. In which case I will have a whole bunch of triangles forming this object, and if I have a deformed object, it will look like this. And the way this works is that for each triangle here, so I have this original shape and the deformed shape of that triangle. What's going to happen is that if I deform a triangle or tetrahedron in 3D, then this object, depending on its material, will apply some forces to its vertices so that it tries to recover its original rest shape. Right? So this is what we call rest shape, and this object in the deformed shape is trying to go to its rest shape. And the finite element method allows us to compute these forces. Now there are different material formulations, there are different ways of computing these forces, but so I'm not going to get into the details of the mathematical formulation, but I think it's sufficient for you to understand how this method works. Is that it's basically some mathematical formulation. Depending on what kind of material model we use here, it applies forces to these vertices. So in some ways, this sort of resembles a mass spring system, right? So these are like the point masses, and we're applying some forces to those point masses. But we're not connecting them with springs, but instead we're connected them with these triangular elements or tetrahedral elements. They are defining the forces applied to these vertices, right? So, but with a mass spring system that we talked about, things are a little bit simpler, and this is what you guys are implementing. Its formulation is quite a bit simpler than finite elements, and it is still used. It is still a viable method for simulating deformable objects, right? Although for a lot of simulations, finite element method would probably give us higher fidelity. So it's more favored more recently in computer graphics. But nonetheless, the mass spring systems have use cases too. So they can be used for deformable objects. They can also be used for simulating brittle objects, not just deformable objects. Well, an example of that would be a fracture simulation. So here's an example fracture simulation. So in this case, we have a whole bunch of particles, and those mass particles are connected by springs, with springs. And these springs are really super stiff springs, so they don't extend that much. And if you extend them a little too much, they can vibrate a little bit, but they don't extend very much. And if you extend them just a little too much, the springs are going to break. And when they break, the neighboring springs break, and the neighboring springs break, and the whole thing fractures in a fraction of a second, forms these really, really interesting fracture patterns. So these fracture patterns, the fracture pattern that's forming here is not pre-computed. This comes out of the simulation. This fracture shape comes out of this mass spring simulation. And this particular way of using mass spring simulation is called paradynamics. And this is, again, a recent simulation work that my student Nia Thorong has been working on. But I'm just showing you that this is a fracture simulation using a mass spring system. Mass spring system, of course, can also be a mass spring system can also be used for simulating cloth and different types of deformable objects. So here's a cloth simulation example, again, from a recent work that my student Nia Thorong has been working on. So in this case, it's just a regular mass spring system, nothing too complicated about it. The only difference here is how these different vertices or masses are connected via springs. So we have different forms of springs that can handle extension and bending and stretching and shear energies. But it's just a typical mass spring system that you guys will be implementing for our last project. But mass spring system can be used for simulating cloth, but typically we use different types of forces than just traditional spring forces in computer graphics. The most common way of simulating clothing in computer graphics would be something like this. Like we will have a triangulated mesh, and the vertices of that mesh would be where our masses would be. But instead of having spring forces that connect them, we typically use different types of force formulations. But conceptually, they're actually very, very similar to mass spring formulations. I'm just saying that they're not quite mass spring formulations because what we apply are not quite spring forces. They're just different. There might be spring forces as well, but we add different types of forces too. Now, what I'm going to show now is just going to be an animation of a commercial product that's using cloth simulation, just to show you some cloth simulation examples in computer graphics. All right, so if the cloth simulation is done right, you should not really notice it too much. In reality, we're used to seeing cloth deform, but we don't really pay too much attention to that, right? So a lot of this cloth motion is going to be quite subtle, which is exactly what's intended. You don't need to be too distracted, right? But sometimes that cloth motion is going to be a little more exaggerated because that's going to be sort of hero content. Over here, for example, it's really subtle, right? And that's what you're trying to do. In this example, the cloth is moving a lot more, and that's what is intended, of course. So these are different simulation examples generated with this particular tool. It's Marvelous Designer. It's a very popular production tool. Of course, we can generate static scenes like this, or dynamic scenes. You sort of simulate a few frames until cloth rests at a position to get these shapes. Very nice examples of cloth simulation. All right, I hope you enjoyed this. Now I'm going to move on to some other topic here. That's going to be fluid simulation. Do you remember this? Now this is mass spring cloth simulation. What I showed you earlier was not necessarily mass spring cloth simulation. But this is interacting with a fluid simulation. This is also a mass spring simulation for the fracture. It's also interacting with fluid simulation. Now, let's move on to how fluid simulation is handled in computer graphics. A popular way of doing fluid simulation is particle-based fluid simulation. As the name suggests, we're going to have a whole bunch of fluid particles moving around. They may be hitting objects, they may be interacting with each other. They're not quite connected with springs because this is not a deformable body, but the particles are still interacting with each other. They're applying forces and so forth. So in this case, the membrane down here is a mass spring simulation. The fluid is the particle-based fluid simulation. We don't always render particle-based fluid simulation like this. We simulate it like this, and then we generate a surface around it, and we form a triangular mesh around it, and we render that triangular mesh with ray tracing, with reflections and refractions, so it actually looks like fluid. Here it sort of moves like fluid, but it doesn't quite look like fluid because I'm displaying the particles, so you can see the particles here. Now, particle-based fluid simulations, another name for it is Lagrangian fluid simulations. So if you hear Lagrangian fluid simulations, people are talking about particle-based fluid simulations. A common method of particle-based fluid simulation is smooth particle hydrodynamics, or SPH. The way SPH works is that for each fluid particle here, I look at a neighborhood around that particle, and I find the other particles around it within that neighborhood. And then I'm going to apply forces between these particles, forces that are exerted onto this particle due to the presence of the other particles around it. So these are all showing forces that are applied to this particle, right? And these forces are computed using Navier-Stokes equations. And Navier-Stokes equations are the governing equations of fluid motion. So these are not quite springs, these are like different types of forces, even though their directions kind of make you think like they're spring forces, but they're not quite spring forces. Like they are, the force magnitude is computed using a different formulation. derived from the Navier-Stokes equations. I'm not even going to show you the equations. They kind of look a little complicated. They're just differential equations. But they are basically this F is equal to ma of fluid dynamics. That's basically what it is. They also add a few other things. It's just that differential equations that define the motion of fluid. And these forces that are applied on individual particles are derived from those equations. And once you derive the force formulation, it's just a matter of finding the neighboring particles around the particle and applying those forces. And then you step through your time step and you get your SPH simulation. That's not a very complicated topic, actually. There are complicated problems related to SPH simulation. For example, how do you make sure that an SPH simulation does not generate fluid that is bouncy? So if I had spring forces, I could create something that's sort of bendy and bouncy and vibrating. And SPH simulations sort of behave bouncy in a way. And that's very distracting because oftentimes we use fluids that are not bouncy. For example, water, we use them for simulating water, and water is not compressible. Well, all right, technically it is compressible, but very, very, very little. For all practical purposes, water is not compressible. And that property is very, very important. A lot of our hydraulic devices are designed around that fact. So you don't want your water simulation to be bouncy, right? At all. And solving that using SPH type of simulation is kind of hard. It's a little bit of an issue. It is possible with some more complicated formulations, but it's a very difficult thing to do. An alternative technique is, instead of trying to solve Navier-Stokes equation using particles like this, it's a differential equation, so I can just solve the differential equation. So a typical way of solving differential equations would be using some grid-based discretization. So that brings us to grid-based fluid simulations. So in a grid-based fluid simulation, I'm going to define a simulation domain first. Let's say this is my simulation domain, and my fluid is going to live inside this simulation domain. And I'm going to take this simulation domain and I'm going to discretize it into some grid or whatever resolution that I want. All right. And for each one of the cells here, there are a whole bunch of cells, right, in 3D. For each one of these cells, I am going to solve the Navier-Stokes equation in this discretization. So basically, you solve for the pressure and the velocity terms, and I'm going to define all of these in this cellular discretization. So one other thing that Navier-Stokes equations define is divergence. That is, if there's no divergence, that means the amount of fluid that goes into this volume from any one of its faces should be equal to the amount of fluid that comes out of its other faces. Right? If that's not the case, then I would be compressing or expanding this fluid. If this is not compressible, right, then like for example water, we want to have no divergence. So we want to make sure that the fluid volume is sort of being preserved here. Like whatever comes in, comes out. And this sort of thing can be more easily solved using this grid-based fluid simulations. And we call these Eulerian fluid simulations. Eulerian or grid-based fluid simulations. Now, these grids don't have to be like regular grids like this. We can form different types of discretizations, but this is a more common way of defining the grid-based or Eulerian fluid simulations. So let me show you an example of Eulerian fluid simulation. It's a relatively old example, but I think it's still a very, very nice one, as you can see. In this case, we have a grid-based fluid simulation that's interacting with a very thin cloth simulation. So it's generating this interesting fluid motion. Now, it could be used for liquids, Eulerian fluid simulations, but it can also be used for gases. In this case, it's a smoke simulation, again, using grid-based simulation technique. And we have used this technique, I have used this technique in my research. We have used it for computing explosions. So this is a grid-based or Eulerian fluid simulation that's computing these explosions. And we're also, in addition to the pressure and the velocities, we're keeping track of temperature in this simulation. And using that temperature, we are computing the amount of illumination that is coming out of this explosion. This work was actually about rendering this, not simulating it. It's about efficiently rendering explosions like this using the illumination that they generate. So there's no external light source here. The entire illumination is coming from the fluid dynamics, the explosion simulation, basically. So explosion simulation defines temperature. Temperature, we convert it to illumination, and that illumination is used for rendering this. Anyhow, so examples of grid-based fluid simulation. Now, grid-based fluid simulations are very good because they can solve this pressure equation and make sure that there is no divergence very nicely. But then they have issues like they sometimes lose volume and mass. And particle-based simulations don't have that problem. So that brings us to hybrid simulation techniques. The hybrid simulations try to combine the strengths of Eulerian and Lagrangian fluid simulations, grid-based and particle-based fluid simulations. With grid-based fluid simulations, I can solve the pressure really nicely. Like, I make sure that the velocity field that I generate here is divergence-free. So my fluid is not supposed to compress. But I can still lose volume here because I have a discretization and I'm going to have some numerical issues here. Like there's going to be some numerical precision limitations here. And because of that, these sort of simulations can have issues with preserving mass and volume. That will be an issue. With particle-based simulations, I don't have that problem because I have particles that are directly associated with some fluid mass, right? They're not going anywhere unless I delete those particles. But I have difficulty making sure that my fluid simulation is not compressing and expanding. So hybrid fluid simulations solve this problem by combining these two methods. So I'm going to have a grid. I'm also going to have a bunch of particles defined inside this grid. And using this, I can have a nice hybrid fluid simulation. So the way that it works is that I'm going to solve some of the things using particle-based representation, and I'm going to solve some of the things using the grid-based representation. For example, advection, that is the motion of the fluid mass, I am going to solve it using the particle-based formulation. In particle-based representation, I have particles with velocities and they move around. Very easy to compute. Super easy to compute. But then I'm going to take these velocities in their positions in the next time step, and I am going to take those velocities and I'm going to project them onto this grid. And this, when I project all the velocities to this grid, it's going to form what we call a velocity field in 3D. Now this velocity field may or may not be divergence-free. If it's not divergence-free, I would like it to be divergence-free. Divergence-free means that whatever comes into a cell must go out, right? And I can solve that fairly easily in this grid-based formulation. I'm not going to get into the details of how a given velocity field can be converted into a divergence-free velocity field. Mathy details I'm skipping. But just trust me when I tell you that it's fairly easy to do using grid-based formulation. And once I solve these velocities, then I can update the velocities of the particles. I can project them back to the particles. So this is pretty much how the hybrid fluid simulation works. Now I'm going to show you an example of hybrid fluid simulation that we used in one of my early works here. It's a collaboration with NVIDIA folks. So this is computed on the GPU using a sparse grid structure. So that the advantage of the sparse grid structure is that we don't have to explicitly store every cell of the grid. It is using a hybrid simulation model. So we're representing all of the particles, but not all of the grid cells. So we can expand the simulation volume as much as we want. And that's what this simulation is showing, that fluid can expand as much as it wants, and can allocate more cells and expand the fluid simulation domain as needed. These were not real time though. They were very fast and interactive, but these are not real time fluid simulations. But we can actually do this sort of simulation real time. So I'm going to show you an example of that. So David Lee has amazing demos, and I'm going to show you some of his demos live here. All right, I believe this is the one. All right, can you see this? Can you see the demo? All right, I hope you can. It seems like you can. All right, so here you can draw some fluid volume if you want to. And then you say, oh, start the simulation. And it's generating this totally interactive simulation live, running in the browser, rendering using WebGL. It's a pretty nice and impressive demo. I can actually, let me see, I can increase the number of particles here so we can get a high resolution. Let's pick one of the presets. Okay, this one. And this is using a hybrid fluid simulation model, just like we talked about. More specifically, it's using the FLIP simulation model. So there are particles, and there's also a grid. And you can interact with it. So you can see handling this many particles, however many this is not that big a deal at all. And it's running on the GPU still. So there's quite a bit of compute power going on here. But it's doable real time. Although if you want to get high fidelity simulations like we would use in movies, for example, you would probably want to have a lot more particles than what's presented here. Still, I love these demos. They're great. Check them out and play with them if you want to. All right, I'm going to stop playing with it now. I'm going to move back to the slides. All right. So we even did a live demo. Great. Not a code that I've written. Just making that clear. David Lee. You can actually see the source code and everything. It's really great. All right. Now, sort of particle-based, at least this hybrid simulation idea of having a particle-based discretization and also a grid, it can also be used for simulating different types of deforming objects. For example, something like a lava, or we did this for another paper. So in this case, we have a solid object, a deformable object, simulated using a hybrid simulation model. And also the lava that's melting this object is also implemented using the same simulation model. And this is, or more specifically, using the material point method. This simulation was also computed on the GPU, but not real time or interactive, but relatively fast. And it can be used for all sorts of different things. The material point method can be used for simulating. It can be used for simulating fluids. It can be used for simulating sort of these gooey type objects. It can be used for simulating deformable solids. It's being used for simulating all sorts of different types of objects. So yeah, it's a very versatile simulation system. Very much the same idea though. Like there are particles carrying certain types of positions and velocities. In this case, they also carry deformations along with them, or deformation gradients. And a part of the simulation is done, and the particle representation, a part of the simulation is done at the grid representation. All right, so all of the stuff that I talked about here, like all these things, they may look sort of different types of things, but they're all, when you look at them, they are using one form of Newtonian dynamics, right? So F is equal to ma is basically what all of these systems are solving, one way or another. So there are different discretizations of the system. Like you can triangulate a model using like FEM, finite element method, or grid-based fluid simulations. use a different discretization, volumetric discretization, or you can solve them using particles like mass spring systems, or SPH, like particle-based fluid simulations. But nonetheless, at the core of them, when you look at them, they are all based on this idea of Newtonian dynamics, right? F is equal to ma is what's driving all of these simulations. But this is not the only way we can simulate things in computer graphics. There's a different concept that doesn't quite use this formulation directly anyway. And that brings us to position-based dynamics. So here's how it works. Now, with Newtonian dynamics, when I have like two masses connected by a spring, what I compute here, like in this system, I have some internal forces, right? So with Newtonian dynamics, what I would do is that I would compute this force, and now from this force, I'm going to be using F is equal to ma, and that will give me the acceleration, right? From the forces, I get the acceleration. And from the acceleration, I would compute the change in velocity. From the change in velocity, I would compute the change in position. So this is what Newtonian dynamics would do. Now, position-based dynamics, however, will not use this. Instead of these internal forces, position-based dynamics uses constraints based on positions. So what do I mean by constraints? So these forces are gone. I'm not even going to look at those forces. Instead, I'm going to have a set of constraints, let's call them C. And those set of constraints, they could be something like a distance constraint. For example, these two particles should be a certain distance apart. It's a distance constraint. It's basically like a spring, right? But it's a distance constraint. And from this distance constraint, it directly computes the change in positions. So it's not doing all of this compute forces from this whatever distance, and then from forces compute acceleration and velocity change and position change. It's going directly from these conditions to the position change. Now, there are lots of advantages of this formulation. This can be unstable. Depending on how you solve the system, this can be numerically quite unstable, right? I've shown you a demo last time with a mass spring simulation. If your time step is not small enough with explicit integration, our simulation was just blowing up, right? And this happens because we have this velocity term here that defines the position. And this velocity term, this velocity change can be quite high because I can have very strong forces generating strong acceleration, and I can have strong velocities, and the whole thing explodes. But with this, I am just going from constraints to position changes. This leads to very, very stable simulations. So these simulations don't really break that often. And you can actually define a lot of different types of materials with this sort of position-based dynamics formulation. So I'm going to show you an example of a unified simulation system implemented using position-based dynamics. And these are some super impressive demos, including fluid simulations and deformable objects like cloth and strings, and also solid objects here that are represented as particles. So this is showing the particle-based representation of the same simulation. Here's another example. This is probably, so there's smoke simulation here going on. Again, just a particle-based representation rendered nicely, and this is the particle-based rendering of the same simulation. And everything moves really nicely and sort of in an expected way, and generating really, really nice simulations, and very, very efficiently too. And interaction of different types of materials can be very easily handled with this type of simulation system. So position-based dynamics is actually a very, very powerful tool that's used more and more often in computer graphics today. So we're puncturing the balloons filled with water here, and the same simulation displayed as particles. It's just a great work. I love that. All right, so this is pretty much what I wanted to talk about when it comes to simulation in computer graphics. Before we end it, though, I am going to show you a recent reel from a software that's used in generating all sorts of simulation in computer graphics. Houdini is a very, very powerful and popular tool used in computer graphics, in graphics production, and I'm going to show you some nice animations that involve simulation generated using this tool. So let's enjoy it. So you can see all sorts of different simulation elements here, different types of smoke and particles moving around, lots and lots of explosions, some fluid dynamics. Fire and smoke and dust, all sorts of particle-based simulations. Different effects of law simulation. Rigid body simulations. So these are basically the same simulation models that I talked about, combined with a very nice software implementation given to really talented artists to generate some quite amazing visuals like this. Yeah, not all of them are physics-based simulation, but most of these videos go with physics-based simulation. Again, smoke, water, and ground simulation is another thing. Flocking. Lots of explosions. Showing different simulation, different rendering layers and simulation layers, of course. All right. Well, I hope you enjoyed this video. I'm pretty sure you would enjoy it a bit more without me blabbering while the video is playing. So if you want to see the original version of that, check it out. I'm pretty sure you can easily find it. It's the 2020 reel of Houdini. These are all recent production examples generated using this particular tool. Thank you for saying that you enjoyed my commentary. I'm pretty sure you would enjoy those videos without me speaking in the background. I'm not even sure you guys can hear me while the video music is playing. I hope that you could. Alright, with that, I'm going to end today's lecture again. Thank you all, and I'll see you all next time. Yeah, thanks.